I'm the mechanical engineer as a mechanical expert from BSF China. I have more than 20 years experience at mechanical engineering. I like mathematics very much because this software helped me a lot to develop so many calculation programs. Also helped me to develop a unique theory for design of tube sheet. This is the topic for today. You can see the title for this presentation is Mathematical Assistance in Developing a New Theory for Tube Sheet Design. Okay, let's start. For this presentation includes 6 sections. First, we will make a short introduction about the tube sheet design, because I think maybe this is a specific topic. We should give you some background, and then we will introduce the situation about the existing theory. What's the default for the existing theory, and then why we need to developing a new theory to solve the problems faced in modern industry, and then we will discuss about the advantages of a new theory. And section 5, as I said before, we also develop a program based on mathematics according to our new theory to to make the design life more easy for the engineer. In the end, we will make a short summary. Okay, let's start with section 1, background of tube sheet design. The shell and tube heat exchanger are extensively in the nuclear power plant process and chemical industry. Here you can see the tubular shell and tube heat exchangers. It's widely used in chemical industry. But I'm not sure you have ever seen this kind of equipment in the plant. But it's very popular in chemical plant or in nuclear power plant. As the tube sheet thickness can be up to 1,000 millimeter, and the diameter can be up to 10 meters for modern industry. As you can imagine, this is a heavy parts and also a very expensive parts. Normally, the tube sheet is forged material from carbon steel or stainless steel. So therefore, the theoretical research for the tube sheet design has received considerable attention due to its importance since 1940s. But this is also a very complex subject in mechanicals. We will introduce why we say this is a difficulty problems in mechanicals. Okay, section 2. We will make a short introduction of the existing design theory for the tube sheet. As you can see, there are so many kind of heat exchangers. In the past, for each kind of heat exchanger, we should develop a unique, or let's say we need, for example, here we have 5 types of heat exchangers. We need 5 different design methods, because you can see the upper part and the lower part of the heat exchanger are totally different. So at the beginning in 1940s, the engineer want to develop a design theory for the tube sheet design, because the mechanical this is a complex mechanical problem. So they want to simplify the problems. They assume the lower part and the upper part of the heat exchanger are same, so that they can simplify the analysis. Because in this case, they only needed to make analysis for half of the unit. As you can see, there are so many unknowns to be solved by mechanics. If you only analyze half of the unit. That means the unknowns, the numbers of the unknowns will be reduced. So the problem can be simplified. Even in this case, we need to solve a differential, a four-order differential equation, as well as a system of linear equations with 12 unknowns. So the tube sheet design is very complex, also time-consuming. Before we, if you do the design without a computer, let's say you do the design by hand calculation. Normally, you need 1 week to make a complete design for the heat exchanger. Also, as we said before, this is for existing theory. They make some simplification. Simplification means you will lose some information for the equipment or for the heat exchanger. And in this case, you get a design result, but this design result may be on unsafe side for sometimes, and sometimes you will get over design. But anyway, it is unpredictable. You don't know where you are. This is the main default for existing design theory. So, but if there is some default in existing theory, that means a new theory is needed, or there is some, how to say, reason behind that we should developing a new theory. As we said before, for existing theory, they assume the lower part and the upper part for the heat exchanger are the same. But in reality, the lower part and the upper part are not the same. Let's say the heat exchanger, we put all these heat exchanger together, we can see if we make a mid plane here, we can find the lower part and the upper part are different. Let's summary this kind of how to say situation. This is, let's say, mid-plane asymmetry. If we can develop a theory based on this idea, then all kind of heat exchanger can be, how to say, designed with, by one unified theory, and also solve the problems due to the simplification by existing theory. Based on this idea, we can we develop the new theory, but you know, the system will be complex compared to existing theory. Therefore, we need to solve a system of four-order differential equations, as well as the linear equations should with 30 unknowns. Luckily, in nowadays, we can use Mathematica, because even you, how to say, you proposed a new design theory, you should make the calculation and get the result and compare with, let's say, experimental result. Or in mechanicals, we have one method named 5-element method. So in this case, so that we can compare over a new theory design result with FEA result, or test by experiment. This is the differential equation in theoretic and the solution in theoretic. Here I just show some code in Mathematica program. Here you can see we have make a four-order differential equation system, and then we can solve the differential equation by Mathematica. And also for the linear equation system, also can be solved by Mathematica, let's say within 1 or 2 seconds. That means the design efficiency is improved greatly. As you know, when you develop a theory, you cannot make the theory in one step, because you should try many, how to say, try different method or different treatment to how to say to adjust your theory. In this case, if you modify something um, in theoretical, that's easy for you modify it in mathematical. Then you can run the calculation again. You can get the result and compare with uh, FEA analysis. In such case, um, we modify our theory step by step. In the end, we can develop a state-of-art theory compared to existing method. Here, I would like to introduce the verification of the new theory. As we said before, we can learn mathematics according to our new theory, but you should compare our result with FEA analysis. Here you can see we select 6 typical heat exchangers and run a calculation. The dot point are the simulation from FEA. You can see our prediction is perfectly agree with the simulation from FEA for, for all 6 typical heat exchangers. In such case, we believe that our new design theory can, how to say, let's say, solve the problems since 1948 and make a unified theory which is suitable for all kinds of heat exchangers. But as I said before that, for different heat exchangers, we need to use different design method. This is a great breakthrough in a theoretic for design of tube sheet. Okay. And in 2021, we submit our paper to the Journal of Pressure Vessel Technology, which is how to say from ASME organization. After peer review for let's say more than 6 months, and then the theory was accepted and published finally in 2022. The peer reviewer said this is how to say the importance of this theory is apparent for the tube sheet design. Now, it's this theory is widely accepted by engineering by engineers all over the world. But the design, let's say, the design is a little bit complex compared to existing theory. So we also need to develop a calculation program. Now, I want to show the advantage of our new theory. As we said before, the new design theory is very accuracy, which is how to say, agree with very well with FEA simulation. We also should compare our design result with existing theory. The comparison between the new theory and the existing theory also performed for 6 typical heat exchangers. You can see the green line is the prediction from existing theory. It is obvious that significant design errors from existing theory. And you can also see sometimes the existing design theory will get, how to say, unsafety design. Sometimes they will get over design. In a word, the errors from the existing theory is unpredictable. Therefore, our theory is not only, how to say, make a accuracy design, but also can ensure the safety of the heat exchangers. As you can imagine, for a heavy big heat exchanger, it's very important for its safety. You know, this equipment also is also very expensive. If if something happened with the heat exchanger, let's say it's burst or failed, which will lead to big money lost. As we said before, because the new theory is very accuracy. In this case, we can get the real stress distribution in for all parts in the heat exchanger. Therefore, based on this correct information, we can do the design optimization. Then we can reduce the tube sheet thickness while ensure the heat exchanger. This means we can, how to say, save the cost and also ensure the safety of the heat exchangers. This is a pic of pictures for a big tubular reactor. You can see the two tube sheet, bottom part, upper part. There are thousands of tubes. In the tubes, there are filling catalyst. The chemical gas will go through the catalyst and make the chemical reaction to make the chemical product. Normally, this kind of the cost for such kind of reactor, for example, if the diameter is 9 meters, the cost will be more than 20 million euro. So this is very expensive reactor. Also, very dangerous reactor. The temperature can be as high as to 400 centigrade. The pressure will be, let's say, 6 to 8 megapar. As you can imagine, if the heat exchanger failed, this will lead to safety issues and also damage, how to say, as life lost. Section 5, as we said before, for such kind of design based on a new theory, without computer, you cannot, how to say, perform a real design. Luckily, we can use Mathematica as a platform to develop a special program, especially for the design of tube sheet. Our idea is very simple. As you know, before design, you should get how to say, get all the design data as input. We make a Excel data file. In this file, you just put all the design data in, and then you can run a mathematical program for tube sheet design. This program can extract all the design data from this Excel file. Then the program can perform the analysis and calculation. After calculation, the program will show you the design report. Let's see how the design report looks like. First, the design report including 3 parts. First, it will generate equipment overview based on your design input, how the heat exchangers looks like, what's the diameter, length, pressure, temperature, something like this. The second part is the most important part for our program, because for engineers always how to say focus or interested in the stress distribution for the parts in heat exchangers. With this kind of distribution graphic, the engineer can make a judgment where is the weakest point for the equipment and how we can make a design optimization later. For example, uh, you can see this is the highest. I will show you later. Part three, we also need to generate a design report for archive. Here, I would like to show you the output. This is the output from Mathematica. First, you can get an overview of this equipment and with the design data here and the stress distribution figure. Just for example, from the distribution for the stress and for stress, you can find that this is the highest stress here. That means in this region, the stress is in high level, so you can make some design change to lower the stress, or this part can be reinforced so that you can also reduce the stress level, but you only need a few material. For example, here is the lowest stress, in the lowest stress level. That means in this area, you do not to enhance the equipment. Based on this information, you can do a design optimization with, how to say, with less cost, or you can save cost. Here, sometimes we also, the engineer also are interested with the, how to say, the deformation of the equipment. Here, the deformation can automatically generated by the Mathematica. Okay, this is the output for our design program. Here, we also want to discuss about the efficiency of a new program. For sometimes the existing theory does not work. In this case, before we develop the new design program, the engineer should perform field element analysis. For such kind of typical fixed tube sheet heat exchangers, the engineer need more than 10 days to make a complete analysis for the heat exchangers. But with our design software based on Mathematica, as we said before, you just need to make, how to say, put your design data in the Excel file and then run a mathematical program. Normally, for one calculation, if every data is ready, the program it takes let's say 30 seconds. If you want to revise the design, you just need to, how to say, modify the data input in the Excel file. Then you can run the calculation again. Therefore, with this kind of program, for one heat exchanger, normally 1 day is enough. Also, you can get a very nice design report with all detailed information you are interested. For FE analysis, you can, how to say, you can get a design result, but you should make your own judgment. Where is the weakest point, or how can you do a design optimization? It depends on how to say, on the analysis based on the experience of the designer. But with the mathematical program, the problem is solved in theoretical. Therefore, it's easy for you to make a judgment, or let's say the program will tell you where is the weakest point and how can you make a design optimization. This is also the reason why we need to develop a new theory, but not just rely on FEA analysis. Uh, um, Even you can perform FEA analysis if you make a wrong assumption or make something, how to say, the edge condition, you make a wrong edge condition, you will get a wrong design result. This means it is highly dependent on the experience of the designer. But with the new theory, such kind of mistake can be avoided and can ensure the design quality. Here is an example for the design optimization for cost saving. This is a tubular reactor. The diameter is about 7 meters with around 9,000 tubes. The equipment weight is about 100 tons. We can do the design optimization to reduce the tube sheet thickness. Before design optimization, the thickness of the tube sheet is about 300. After design optimization, we can reduce the tube sheet to 200 around. That means that means the weight of the tube sheet is reduced greatly, means material saved and also easier for future fabrication because there's 9,000 of holes to be drilled on the tube sheet. And also for heavy forged material, if you want to get a heavy thickness forged material, the quality will be, how to say, let's say it's not easy to be ensured, but with the thinner thickness of the tube sheet, the quality of the forged material can be ensured. Okay, now I would like to make a summary for our work. We think Mathematica is is an excellent tool, not only for theoretical study, but also an excellent platform for engineering. With Mathematica, we can build or modify our theoretical model in a short time. With the help of the Mathematica, we can develop a state-of-the-art theory within 12 months. As I assumed, if we cannot find a suitable calculation tool like Mathematica, this kind of new theory cannot be developed within 2 or 3 years. Okay, this is my presentation. Thanks for your attention. Now, is any question from your side? Is there a modern library for Tubesheet? What's mean library? With Mathematica, we just do the calculation, not modeling. For example, for Tubesheet, you just need to input the diameter, how many tubes, tube hole in the Tubesheet, and what's the diameter of the hole, and also the thickness. You just put some numbers in. For material, you should input the material properties as input. For example, the stress, allowable stress of the tube sheet material, also the density, elastical modulus, something like this. Anyway, all the information you just need to input in the Excel file, and then the program can get the delta and run the calculation. This program just interested for very specific engineer. It's not so popular, not like Word, Excel. It's very widely used.
Right. Matt, we're all out of time, so
Thank you.
yep.
So thanks for your attention.